All right, well, let's get to it. So, what we were talking, oops, wrong folder. Um, what we were talking last time, right? Polar coordinates. So it's time to do calculus with polar coordinates. Um, before we do that, let me do one quick view here. So suppose we can take something that's polar and make it into something that's parametric by that, right? So we know that if you've got a polar function would be something of the form r equals f of theta, where the right-hand side only depends on theta as a function, okay? And what was the conversion between polar to Cartesian? It was that x would have been r cos theta and y would have been r sine theta. Okay, great. And so if I wanted to do, if I know that r is given by some function of theta, I can just substitute that in and I get f of theta cos theta and f of theta sine theta. Okay. Um, and great. All right, so does that make sense? Yeah, based on what we did last time. Okay. Now the benefit of doing this or looking at it in that way is that we can actually answer the first question, calculus related question, which is slopes of tangent lines. Okay, so the slope of the tangent line is dy dx, right? Okay, so what is dy dx? Well, it's dy d theta divided by dx d theta, right? That's the chain rule. Yes? Okay. Well, what is dy d theta? Well, we've got y equals f of theta, so what's the derivative of f of theta sine theta? What do we have to do? Uh, not chain. Jack? Product rule, okay? So it'd be the derivative of f of theta sine theta would be f of theta cos theta plus f prime of theta sine theta. Okay, so the top there is dy d theta. Gucci? Okay, similarly, we got to do the same thing with dx d theta. So what's it? That, right? Okay, and the first term is minus in this case because well, the derivative of cosine is minus sine, not sine. Okay, so that thing is our derivative, or rather the slope of our tangent line. Okay, okay, so does that make sense? Yeah. Okay, so good. Now, well, if dy d theta is 0, that means that this whole fraction is 0 over something, which is 0, right? Which means that what? Means that the slope of the tangent line would be horizontal. or the tangent line would be horizontal, slope would be 0. Okay, what about if dx d theta is 0? Yeah, it's vertical because the slope's undefined. If they're both 0, we have a bit of an issue. Okay, if they're both 0, then our slope is 0 over 0, which is not a specific number, right? That's an indeterminate form. And so what usually this means is that either there's a discontinuity or an asymptote or something like that, or a cusp, okay, where a cusp, like a sharp point. Yeah. So, like, for example, in Cartesian coordinates, absolute value of x was a good example of this, right? That what is the derivative for x negative? It's -1. For x positive, it's +1. But at x equals 0, what's the derivative? There isn't one. It's undefined. Okay, so that can happen here too. So you just have to worry if they're both 0, then you're in trouble. If only one or the other is 0, then that's no big deal, right? You either have a horizontal or a vertical tangent, and that's perfectly fine. Okay. So that's question number 1 is how do we talk about slopes? Well, there you go. Okay. Um, right. Okay. So that's the easy question, right? Is slopes. What else could we ask about doing things in polar coordinates? Okay. So what kind of stuff have we done in calculus with Cartesian coordinates? We did derivatives to talk about slopes. What else did we do? Integrals to talk about area under a curve, okay? Or area between a curve and the x-axis. So what's the polar version of that? That's our quest today. Okay, does that make sense? Or at least a question makes sense? Okay, so doing things in polar coordinates is going to be a fundamentally different view of area. So let me take a random polar curve. Okay, that's given by some polar function. Okay, now, I mean, there is the x-axis, right? But the x-axis is a Cartesian sort of concept. Okay, so instead of thinking about the area between the curve and the x-axis, what I want to do is I want to think of the area swept out by the curve as we move. Okay, so for example, let me draw here in blue. Okay, so there is some area that has been swept out by my curve, right? And so my question is, what is that area? Yeah? Okay, now it's some big blobby shape. And so if we're going to really use calculus to do this, what I want to do is think about slicing that area up into a lot of really tiny pieces, figuring out the area of each piece, and then adding them up. Yeah?
Why isn't it the strategy to like take the 2 points
Mm-hmm.
and then make the y value equal to the x-axis or wherever you like the lowest point and just doing it like that?
Oh, okay. No, I see what you mean. Um, so, well, okay, because that isn't the same area as what I've drawn, right? What you're describing is basically take a, let's say, a green line and connect the 2 points and then rotate the whole figure so that that straight line is the x-axis, and then use regular calculus?
Well, are we not trying to find the area under that curve?
No, we're trying to find the area between the curve and the origin. Okay, so the word under is not relevant anymore. Okay, does that kind of make sense? Right? Okay, so what did we do in Calc 1 to start defining the integral to answer this question of area? We took the curve, we drew it, we carved it up into a bunch of little rectangles, and then we figured out the area of each rectangle, we added it up, and that gave us an approximation, right? Then what? Well, we said the more rectangles you do, the better your approximation gets, and then we threw a limit in front, and bam, we got the full answer, right? The correct answer. Okay, so what we need to figure out then is how am I going to carve this thing up? Well, I'm not going to carve it into rectangles because rectangles are Cartesian. We're being polar. So what could I carve this thing up to instead? Well, yes, okay. But I'm going to carve it into little pizza slices. Like so, okay? And now, obviously, there I've drawn kind of really fat pizza slices, but we get the idea. Okay, so what does a pizza slice look like? Well, okay, that was a stupid question. Um, huh? Yeah, well, huh? Why does Pizza King do square cut? I think there's one in Ladoga now because everybody in Montgomery County Chatter, which is like a Facebook group, was like beside themselves when the new Pizza King was opening. Yeah, this is Montgomery County, okay? We don't really have the highest of standards. You know, if you get me a good like wood-fired pizza restaurant that has a good wine selection, like I don't know if there's anybody been to Napoli's in Indy, like at the Fashion Mall. Oh my goodness, that is pizza. Yeah. Uh, it's off of the food court. Yeah, it's like it's indoor seating restaurant, but it's off of the food court. Yeah. Anyway, that's pizza, and their gluten free is actually really good. I'm not gluten free, but sometimes I dine with people who are, so that means I have to be gluten free because you can't you can't say I want it half gluten, half not gluten. It doesn't work that way. Hmm. Yeah, it's not like yeah, it's not like half cheese, half pepperoni, right? You can't do that. So yeah. Um, anyway, what to get me sidetracked? Yeah. All right. So our pizza slices, right? You guys convinced those are pretty good looking pizza slices? Right. Okay. So yes, make them smaller. But what sort of theoretically is the ideal pizza slice shape? Yeah. Okay. Would you guys agree that? So let me draw sort of my ideal pizza slice. Okay. So now a given curve is not perfectly circular. It might be by luck, but it isn't in general. Okay. However, what happens if I make my slices really, really narrow? It's kind of the same thing we did with Cartesian integrals. We said, okay, you've got a curve. If I carve it into a bunch of really tiny pieces, then the curve might as well be straight on that little segment, right? It's so close. All right, so the polar version of that would be to say that a curve in a very, very small window looks circular. Okay, so this is my ideal pizza slice, and I've labeled it, well, how long is the pizza slice? Well, it's whatever R is. Okay, how wide is my pizza slice? Well, it depends on how big I make that angle. Okay, which I've labeled here as d theta, anticipating that I'm going to have like an integral in a minute. Okay, so is that okay? Yeah? All right, so my question for you is, what is the area of my pizza slice? Well, what would the area of an entire pizza be? That'd be the area of a circle, right? Well, what's the area of um, sorry, yeah, pi squared. Okay, so the area of my pizza slice is going to be. This is probably going to drive you guys crazy. 1/2 r squared d theta. Okay, now why 1/2? Well, okay. So yeah, you're asking where's the pi? Right. It's pi if we talk about the whole circle. But how is theta, or therefore d theta, measured? It's in radians, so it's in something times pi, right? Okay, so the pi is sort of hidden inside the angle. Now, why the hell the 1/2 part? Well, yeah, okay. That is the harder thing to explain. Okay, if I zoom in, doesn't my circular piece actually look straight? Right? So for a very, very, very small window of the picture, I'm not actually talking a pizza slice that has a circular end, but rather one that has a triangular end. Okay? So, what is the area of that triangle? Well, this is a triangle, and let me redraw this a little bit. Oops, sorry. Oops, sorry. Just let me draw the damn picture, please. Just give me a minute. Yeah. Okay. If I subdivide this thing like that, then I can get me a right angle, right? Okay. So what I need to know then is, what is the area of that triangle? Okay, so I'm going to redraw it here, right? What is this angle? It'd be d theta over 2 because I split my figure, right? Okay, what is the length of my base? It's r. Oops, dang it. Okay, there's r. Okay, then if I want to know the area of this triangle, I need to know what the other leg is, right? So I could do a base times height over 2 type thing, right? Okay, well, you guys probably don't remember this, but what's the formula for the, well, okay, what's the perimeter of the circle? 2 pi r. Okay, so the perimeter of this piece is r d theta, okay? Because what about if d theta is 2 pi? That means that I've swept out the entire circle. Yeah? What? Yeah?
So are we basically making, so let's say d theta was 30 degrees.
Okay.
Are we basically making a 12-sided shape that acts like a circle?
Yeah. Yeah.
That's all I got.
Right. Okay. So we're looking at one piece of that 12-sided shape.
So it's like close enough.
Yeah. Okay. So do you guys buy that the blue line, which is the straight like if the pizza slice had a straight back versus a curvy back, that the circle part and the blue line part are pretty dang close. Okay, so that if I were to zoom in and take a limit, they'd basically be the same. Yeah. Okay. So what is the length of the black arc, the circular arc at the back of my pizza slice? Well, what is the circumference of an entire circle? An entire pizza would be 2 pi r, right? Okay. What about if I only have a part of a pizza? It'd be some proportion of 2 pi r, right? So it'd be r times some angle. Well, what angle do I have? I have the angle d theta. So that arc along the edge has length r d theta. Okay, do you guys buy that? Okay, so if that length is r d theta, what is this length down here in my half slice? Right, it'd be half that. Okay, this is a right triangle, so what's the area of this? It'd be 1/2 base times height, right? Which is what? Okay, but this thing is really half of my pizza slice, right? Pizza slice equals 2 of these little slivers. And so the area of that pizza slice is approximately 1/2 r squared d theta. You don't seem convinced, Mr. Trabb.
No, I was convinced when you wrote it the first time.
Oh.
Are you teaching to convince me?
Well, what else would I be doing?
Give me options. Let me choose my own.
You can do that in philosophy class. You can't do that in math class. Sorry. Sure.
So I can understand why the green line is R.
Right.
What happened?
Okay, it's approximately R. Right. Okay, now in my pizza slice, the green line is not quite R. It's a little bit short. Right. Okay, but if I make d theta really, 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 really small, then it approaches R in a limit. And that's exactly what I'm doing, right? Because if I write d theta, what am I really thinking here? I'm thinking of setting up a limit. As delta theta goes to 0 and I make the slices really teeny. Yeah? Okay. Right. So maybe think of it this way, right? You're going to take a figure and okay, so let's say you order a pizza, okay, for your frat. How is your pizza carved up? Okay, generally 8 slices. You get a large pizza from, where do you guys order pizza from? Domino's? Yeah, okay. Greek's pizza's pretty good. Yeah. Yeah, if you want to be cheap, then Little Caesars. Okay, so you order your Domino's pizza, your large Domino's, and it's generally cut into 8 slices. Okay. What about if you get like an XL or something? Sometimes it's cut into 12s. Okay. When before coronavirus, when we had like lunchtime talks and we'd order pizza for the audience, we would often ask the pizza company to cut it into slices of 12 or into 12 slices, because then you can feed more people with an equivalent amount of pizza, right? Sort of. It's a trick. Well, exactly, right? Because sometimes you don't want, if you want two pieces of an 8 sliced pizza is a quarter pizza, but pieces, blah, 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 blah. 2 pieces of a 12 sliced pizza is not as much, And maybe you're satiated by that, right? Okay, so imagine if you could call up the pizza company and you could say, all right, I want you to cut it into 1,000 pieces. Then each of those pieces is going to be pretty much a triangle, not a pizza slice with a circular back, right? It's going to be really close to a triangle. That's basically what we've done, right? And so what we're really doing is calling the pizza company and saying, okay, we want you to take the limit as the number of pizza slices goes to infinity. Now, they'll probably hang up on you, but, and of course, who calls to order a pizza nowadays? You don't use the app? Oh, you're old school. Well, okay, right. All right, so that's the basic idea here. Okay, so does that kind of make sense? Right? All right, so let's take an example. So let me pop open Mathematica and let's look at an interesting example. All right, and then I want Mathematica, window capture, 5. Okay. Through the floor. The table legs. Yeah, the table legs are hollow and the power goes through those into the floor. Right. So these tables were designed when the building was, and the electrical was laid out when the building was renovated precisely to be able to do this. So yeah, we used our noodles for, well, they used our noodles. I wasn't here yet. Okay, so let me just take, for sake of example, let's do one of those polar roses that we did last time. Okay, so we had f of, I'm going to use t instead of theta. And let me blow this up so you guys can actually see it. Okay, so I made one of those things last time, right? Yeah. We want to compute what's the area inside of, say, one of those petals. Okay, and if we did that and multiplied by 4, then clearly we get the area of the whole thing. Okay, so what I need to do, though, is I need to know for 2 values of t, or theta, really, where does this thing hit the origin? Okay, and what did we discover last time? How much angle encompassed a petal? It was pi over 2, right? Okay, and so, for example, the first part of the petal, this little segment here, was that, right? Okay, so let me actually do some fancy stuff. Just let me drive. Yeah, let me drive, relax. Huh? Watching me Mathematica? Okay, so if we go t from 0 to pi over 4, then that sweeps out the red part of the curve. Okay, now if I find the area that's enclosed by the red part of the curve, that would be the part of the curve between, that would be 1/2 of that petal, right? Okay, if I find that thing and then multiply that answer by 8, do I get the whole entire clover? Yes, okay. So let's find the area of that petal. Well, what's the angle range for that petal? It's from 0 to pi over 4, right? Theta equals 0 is out here, and then we sweep around to theta equals pi over 4 as we come inside. Yes? Okay, so what do I need to do? I need to set up an integral from 0 to pi over 4 of 1/2 r squared. What's r in this case? F of t. Right? So it'd be f of t squared d theta, but what am I using instead of theta here for? I'm using t just because it's easier to type. Okay, so 1/2 r squared d theta is the thing we need to integrate to get the area, and then the part that we're considering is where the angles go from 0 to pi over 4. So that's sort of 1/2 of a petal, and then we'll multiply this answer by 8 in the end. Okay, does that make sense? The setup? All right, well, so let's see what it is. Okay, happens to be pi over 16. Okay, so if it's pi over 16, what's the area of the entire flower? Pi over 2, right? Because our petal that we just computed was 1/8 of the true thing, right? All right, does that make sense? All right, so let me actually throw one more thing on here for giggles. Oops. So what's the area inside the flower? Pi over 2, right? We just did the integral and multiplication to figure that out. What's the area inside the orange circle? Pi. So what have we discovered? The flower is half the circle in terms of area. Does that look reasonable? Yeah. I mean, to some extent, that's a silly question. It doesn't matter if it looks reasonable because it's true, right? You can't argue with true math. I mean, you could, but then you'd be coal. Oh, burn! Yeah, I know. Okay. Okay. Good. All right. So that's area. Now, let me just double check one thing here. Okay, so where this gets a little bit more complicated would be, let's say that we did the same deal, but instead of cosine of 2t, let's just say that we were doing cosine of 3t. Okay, because then our figure is that. Okay, now, so if I want to find the area of one of those petals, well, let's get half the petal. So you see how the red part is overshot? What should I have gone up to here? Not pi over 4, but rather pi over 6 in this case, yes. Okay, and so what should I change my integral to here? Just 6. And then I get pi over 24. What do I multiply that by in this case? 6, not 12, right? Okay, so if I multiply by 6, I get pi over 4 is the area enclosed by this guy. Okay, which is smaller than the area enclosed by the previous one. That's interesting. Okay, but watch this. What about if you said, oh, well, the total area would just be to go from 0 to 2 pi, right? Okay, so what's the total area that we've talked about here? Pi over 4, right? Okay. But if I integrate from 0 to 2 pi, I get pi over 2. Why? Exactly. So what happened when we drew this thing? If the coefficient of t was an odd number, what actually happened is it drew the 3-leaf clover twice. Okay, so if we integrate from 0 to 2 pi, we've actually double counted all of the area, which is why we got double the number that we did a minute ago. Okay, so you have to be careful to make sure that you're not accidentally double counting area. Okay, the other thing would be, here we found the area between a curve and the origin. What about if we wanted to find the area between two polar curves? Well, we'd have to do some sort of subtraction type game, right? We'd also maybe have to worry about where the curves intersected. Okay, so all of those sorts of usual bits are still on the table. Okay, now what I really want to talk about though, why do we care about doing area and polar coordinates? Well, let me tell you about my buddy named Kepler. So who's Kepler? Yeah, an astronomer. Okay, and so let's go way back. What was the Greek conception of the cosmos? What was at the center of the universe? The Earth. Okay, now that's not quite true if you read Ptolemy, right? Because of the equant, but
Forgot the P.
huh?
Ptolemy.
Wheat thins. Say wheat. Say wheat. Say thins. Say thin. Say wheat thins. Wheat thins. Why are you putting so much emphasis? No. Okay. Yeah. Okay. So what was the ancient Greek conception of the universe? Was that the Earth was at the center and everything revolved around the Earth. Okay. Now, if you look up at night, at the night sky, that actually seems pretty reasonable, right? It sure looks like everything's going around the Earth. Okay. So there were three problems, though, for this model. What are those three problems? The sun, the moon, and the so-called planets. Okay, so the sun and the moon, right? Pretty obvious what the issue there is. What about planet? What the hell does the word planet even mean? Yeah, okay, planetes in Greek means wanderer. Okay, so the planets are so called because they are wandering stars. Now, if you look up at the night sky, okay, so forget the moon, right? What do you see? All of the stars are all in exactly the same spot relative to each other. And that whole, it's as if the entire universe is a giant sphere with the stars painted on the inside of it. And that whole thing is spinning around the Earth. That's what it looks like. Yeah? And that's fine, except for there are four of them. Five of them. Okay? That didn't do that. What were the five? Mercury, Venus, Mars, Jupiter, and Saturn. Those are the ones that are observable with the naked eye. Okay? What did they do? Well, it's not like they were just wandering around as if they were drunk, like, go home, Jupiter, you're drunk, right? They mostly went in the same direction as the rest of the stars, but every now and then they would turn around and go backwards relative to the rest of the stars, and then they'd go back forward again. And so they'd kind of do this like dance through the sky, hence wandering stars. Okay, so the question then is, how do you mathematically explain or predict where these things are going to be? Well, the ancient Greek conception was, okay, I will put the Earth at the center. All the stars revolve around it. The sun and the moon do the same thing. Okay, ish. Um, and then for these wandering stars, how do I get that backwards bit? Well, essentially, what Ptolemy did was he said, okay, I'm going to put these things on epicycles. Okay, so what that means is maybe they go around in a circle, but they're going around in a circle that itself revolves around that circle. Okay, so it'd be kind of like, think of it this way. The Earth goes around the sun, right? The moon goes around the Earth. So if we imagine that the sun was where the Earth is, uh, then the moon is going in a circle around a thing that's also going in a circle. And so what kind of pattern do you get? You get like how many of you guys played with Spirographs when you were kids? All right. Do you two, let me show you a picture of one. Maybe it has a different name for you.
Say I played with Spirographs.
Nobody assumed.
Yeah, I don't know.
Don't double back.
Did you ever have one of those things as a child? No? Have you ever seen these before? No? Okay. I've got some in my office, so I'll show you guys sometime. So anyway, the point though is that they said, okay, well maybe we can sort of approximate the path of the planets by doing this sort of thing. Okay, and Ptolemy spends an entire book doing this sort of thing. It's called the Almagest, and it, you know, pretty well works. It's not perfect, but it never is. And in particular, it wasn't perfect because, well, people didn't live as long, so you had incomplete data. And also, it's a planar method. You'd have to do some stuff to get the planar variations. But, it actually works, right, for the most part. Ptolemy's theories and the mathematical astronomy of the time, they could predict eclipses, right? That was a pretty big deal. Right? If you're about to go to war and suddenly the sun goes out for 5 minutes, like you kind of question yourself if you're like a polytheistic primitive culture, right? Okay, so like that was a pretty big deal to be able to predict when that would happen, huh? Well, Columbus did a lot of things, many of which we cannot talk.
He said, if you don't like leave this land, like the gods will curse you and like it'll make it dark or something, or the sun will be like this, or it was like during an eclipse.
Oh, I don't remember this. Yeah. Mm. Well, the closest thing I can think to is Leonidas at Thermopylae, right? Xerxes saying, "Our arrows will be so many that we will blot out the sun," and then, yeah, okay, because I have no idea what you're talking about. This is what happens when you get old. Okay, all right, so it works for short periods of time, and then the problem is that you build up inaccuracies and things don't match observation. Okay, so flash forward 1,000 years, basically, to Copernicus. All right, so what does Copernicus do? Okay, sun is the center of the universe, and therefore everything moves in circles around it. Circles, okay, centered at the sun. And that's pretty dang accurate. Okay, um, it works, right? Now there was a mild bit of heresy involved because it means that the Earth isn't the center of things, and that kind of caused some problems with certain religious groups, namely the Catholic Church. Okay. But that said, mathematically it works. All right. Now, at this point, though, there's no reason to suppose that the universe actually was shaped that way, right? So there's mathematical model and actual universe, and the two don't have to be the same thing. It'd be nice if they were, right? Because then you'd be describing the actual universe instead of just some mathematical toy. Okay. Well, okay. You look up at the night sky. It appears to you that all the stars are spinning around the Earth. But does that mean that that's exactly what's happening? No, right. So your cosmology, your mathematical model of it is as if everything's spinning around the Earth, even though that's not actually how it happens, right? So the way you model it and the way it actually is aren't necessarily the same thing. But if it tells you where to look in the sky to find a star, do you really care? Well, in some sense, no, and in some sense, yes, right? From an epistemological standpoint, you do. From a knowing where what star is, you don't. Yeah, I know we're getting very philosophical today. I'm sorry. Okay. All right. So Copernicus, circular orbits of everything around the sun. Now, then the problem is, what do you do with the Earth? Because the stars appear to rotate around the Earth. If you make the sun, the Earth not the center, then you need to say, okay, the Earth itself is rotating, because otherwise the stars wouldn't appear to rotate. Okay. Was there any evidence for that other than like any observational evidence for it? Not until Foucault, right? Foucault's pendulum. Okay. All right. Now, that said, let's take this circular model and let's apply it, say, to Mars. It works pretty damn well. But Kepler noticed that it was a little bit off, just a little bit, like 17 arc seconds. This is a very tiny amount. Okay, now at this point, right, you have telescopes, which means you have much more precise measurements of positions of things. Okay, so what did Kepler refine Copernicus's model to do? He said, okay, well, maybe it's not circles, but rather ellipses. And the sun isn't at the center, but rather at one of the focal points. Okay, now Mars's orbit, or Earth's orbit for that matter, is pretty dang circular. It is elliptical, but it's really close to being a circle. Okay, so that brings us to Kepler's laws. If we think of the planets as revolving, including the Earth, as orbiting the sun, where the sun is at the focal point or one of the focal points of that ellipse, then how fast do they do it? Well, what was one of Kepler's laws? It sweeps out equal area in equal time. When I say area, what do I mean? I mean one of these polar freaking areas, a 1/2 r squared d theta. Okay, so essentially what Kepler's law, one of Kepler's laws says, the equal area and equal times one, is that 1/2 r squared theta dot, okay, so d theta dt, is constant for all orbits. Okay, and I could convince you that this is true. Now I need like another 2 hours in a planetarium, um, but yeah, okay. Um, so why we care about doing polar stuff is because, well, and the area within it, right, is this is the kinds of tools we need to do properly orbital mechanics and any kind of physics that has anything to do with polar looking stuff, right? And a lot of times it's way easier to describe things in polar coordinates than it is in Cartesian coordinates. Okay, so that's sort of the, like, there's, 3,000 years worth of mathematical astronomy summed up into 10 minutes. Um, okay, so, right, that's probably a good place to stop. Y'all's minds blown yet? Yeah, okay. All right, see you guys later. Have a good weekend. And let's quit the stream. Have a good weekend.